This is a class on radioactivity, and we know most times students have always complained about questions regarding radioactivity and nuclear reactions, especially when it has to do with calculation. So, and this has been a major concern for most of them. They have not gotten the right concept on how to solve this question, or how to, or on the understanding of this particular area. So let's define radioactivity. Sorry, need to change this marker ink. So radioactivity is spontaneous decay. When we say spontaneous, it's something that is not something that just happen on the go or at once. It happens gradually. So it's a spontaneous decay or disintegration of unstable nuclei of an atom, of stable nuclei of an atom. Sorry. So it's bad already. So now let's look at, let me write it. Radioactivity. Sorry, I have bad markers today. Let's get in tune. So what is radioactivity again? We'll look at it this way. Spontaneous decay. The spontaneous decay or disintegration of an unstable nuclei with the emission of alpha, beta, and gamma rays, and large amounts of heat. So this is radioactivity. A radioactive nuclei or an element are those elements that spontaneously emit radiations from their nucleus. Example of radioactive element. So radioactive elements such as thorium, radon, radium, polonium, uranium. All these are all radioactive nuclei because they have a very large mass, a very large atomic number. And one of the things you have to note is the moment your atomic number is greater than 82, the element is unstable, with an unstable nuclei. So conium is also part, radon is part. I think I'm writing that. So let's look at the types of radiation. We have three types of radiation that we see in radioactivity. The first one is the alpha decay, alpha particles, beta particles, and gamma particles. Let's look at how they interact, or their interaction with magnetic and electric field. If this is my radioactive sample, this is my radioactive sample, and this is my photographic plate. If this is my positive charge area and this is the negative charge plate, this is the photographic plate, the beta particles will deflect towards this. This is the beta particle, and the alpha particle will deflect towards this. The only particle that do not deflect is the gamma radiation. So the gamma radiation does not deflect when placed in an electric field. When placed in an electric field deflection. Or if it is to be in a magnetic field, for magnetic field, let's say I have these two, and I have a magnetic field. I also have this. This, let's say, this is my north pole. This south pole. The beta moves towards the north pole with great deflection, and alpha, this is the alpha, then the gamma does not deflect. This is the magnetic field, deflection in magnetic field. So once you understand this, let's quickly move and tell us what we know, we understand by the decay curve. So the ones that move to a negative are the alpha, or to the south pole alpha. The ones that move towards the positive place or the north pole are the beta particles. So you will see that there is much deflection. It's very strong deflections towards the north pole from the beta particle. Then a slight deflection towards the south pole from the alpha particle. Now, okay, let's look at some other things. Some of the method of detecting this reactivity, we have the photographic film, which I've explained here, the gigamolar constant tube, we have the electron cloud chamber, we have the semiconductor detector, we have the decatron counter, we have the pulse electronic electroscope, and we also have the solid state detector. Now let's look at the types of radiation. Okay, before I move to types of this radiation, let us look at the decay curve. Okay. Types of radiation. Types of radiation. Number one, we have the alpha decay. In alpha decay, this is the kind of equation we have for alpha decay. We have the S, this is the parent nuclide. Parent nuclide with ZA decaying by alpha. This will give us a daughter nuclide of A minus 4 and Z minus 2. So this is the parent nuclide. This is the daughter nuclide. And this is the alpha particle. Alpha particle is the helium atom. So if we have an example of this, let's look at radon, Ra 22688, decay by alpha particle. You may say something like this, or let us just write it as 42 Hb. Please remember there is always emission of heat in this case. So we have radium. This is radium. Is decaying by alpha particle to radon, and radon is also 22286 plus large amount of energy. This is alpha particle. This is an example of alpha decay. So note that whenever you have your parent nuclide, just take away. Sorry, this is an error. Note, it is Z that is here. I just saw that now. Take 4. The daughter nuclide will be a decrease of 4 at the mass number, and a decrease of 2 at the what do you call this? The proton number or the atomic number. So that is that for alpha decay. Let's look at beta decay. The second one, let's look at the beta decay. The beta decay we want to talk about here is the post-electron, because there are two types of beta, and that is 0 minus 1e. So that's the symbol for it. So the parent nuclide is AZX to give you 0 minus 1e. So this one will remain the same, but there will be addition of 1 to the daughter nuclide. So let's look at an example of 11 beryllium. 11,4 beryllium. I hope you can see this very well. Is it enlarged very well? 11,4 beryllium with beta decay will give us 11,5 boron. So, and this will be with an emission of high amount of energy in form of heat. So you must note that the also here. The second part of beta decay positron. This is positron. For positron is quite different from the electron. Positron is the positive part. So we have O1e. So if we have A, ZX, when it moves to this, O1e plus A, Z minus 1, Y plus Q. So, we also have, the only difference is that Z changes by a decrease in by 1. Then we have the gamma decay. Please let me say this one is 2b, this is 3. For the gamma decay, in gamma decay, what we have is, let's say this is the parent nuclide, excited. It gives us back the daughter nuclide, now normal, but with emission of radiation. So, an example of this let's look at cobalt 6027. When it's excited, it still forms 6027 beta nuclide plus emission of gamma and heat. And that is how these are the various questions we have here. Let us take some example. Let us take one example. How many particles? This is 2016 question 46. 2016 question 46 says, how many particles are emitted in the radiative decay of 79 gold to 198.80 mercury. 198.80 mercury. The first thing is, we know that there was an increase in the atomic number. No increase in the mass number. There is an increase in the atomic number. So we can say this is AX, AZ gives us Y, AZ plus 1, and the amount of this with 0 minus 1E. So this is a beta particle. So in that case, so we can say 198. The only thing that has been lost here is beta particle. That's how to find out those things. So they are very, very simple questions. Once you understand these formulas here, then you do not have a problem. So in the next class we'll look at, okay, let us take this question. A nuclide 202, this 2000 question 47. A nuclide 202Y88, 202Y84 emits in succession an alpha particle, and beta particle in succession. That means one after the other. The atomic number of the resulting nuclide is atomic number. So we are looking for the resulting nuclide. Let us do something. The resulting nuclide atomic number. So we are looking for the Z of this. So in this case, we have 202, 84, Y. If it emits beta particle, alpha particle first. So what we're going to have here is 202 minus 4. That will give us 198. Then minus 282. Let's call this one still Y. Then this 198.82Y also emits by beta emission. So this is equal to 198.83Y. In this case, the Z that we are looking for is equal to 83. So these are a few examples of types of decay questions. So the moment you understand the formula, you'll be able to dance around how to answer such questions. Now let's quickly look at the decay curve. The radioactive decay curve. Radioactive decay curve. The curve of the number of particles, the number of atoms against the time. The negative graph. TR, TR, TR. So we can define this is the original and this is the last one. Okay, so now we can define half-life from here. That the half-life is the time taken, half-life, time taken for a radioactive element, to decay to half of its original mass. So that is, if I have 500 grams and the half-life is 10 days, after 10 days, the time, that 10 days is the half-life. That means the mass, that particular 500 gram mass that I had initially would have decreased to 250. And after another 10 days, it would have decreased to 125. And this is what we mean by half-life. So the time it takes for a radioactive element to decay to half of its original value. So that's the half-life. And let me use this to round it off because of time. So it is there. There is where we now talk about A naught, what it means. So in the next class, I'll be dealing with this equation. So thank you for watching. God bless you. Stay tuned, subscribe, comment, like and share this video for more content. Thank you. Have a blessed day.